Okay, so there is only one thing left to explain, and it is about the projection operator. So the projection operator is guaranteeing that we don't get outside of the boundaries, the constraint that we defined. Because here, this arrow is pointing us toward this minimum, but we don't know, there is no guarantee that we don't get to values that are outside the allowed ones. So let us assume that our big theta is defined like this, is this interval. So now I'm starting exactly on the border. So I don't know if I'm getting out of the left side or not. So I shouldn't, because the law is made in a way that I'm taking smaller and smaller steps, but actually there is no guarantee. So a way to avoid that I get out of that is to introduce this projection operator. Actually, another reason for that is if we assume that the fault is matched, in the residual dynamics we have this term only. But if the fault is not matched, in all these equations we don't have the function phi L, we have the function phi some other index. So we never get to write this, which means whatever value we provide to our theta L, it is not going to make a difference like this one going to 0. And this is bad because we are trying to learn a parameter theta, which actually has no effect on making this small. And we can end up in the situation that our learning law is moving theta continuously, but we will never get to a minimum because there is not a minimum in this case. So whatever value of theta, when the fault is not matched, it is not making the residual small. And this is causing a phenomenon called parameter drift. So you're trying to learn a parameter that actually has not effect on your error term, and so you continuously update it moving in some direction, and this can get unbounded, basically. So a way to avoid that is to introduce the projection operator. So we know that all valid theta should stay inside this big set, that now we just drawn it as a ball. Well, we enforce that. The projection operator is enforcing that. And to do that, we need to introduce yet another assumption. The assumption is that the shape of the domain theta is actually a ball. It is a hypersphere. And the radius is equal to m theta hat. And the projection operator is defined this way. So if theta hat, the one that we compute for the next step here, using this update law, is inside, so if its magnitude is less or equal than m, you do nothing. So the result of the operator is the parameter itself. But if we get outside, then we take these and we scale it down by the ratio between the radius of the hypersphere and the actual magnitude of the parameter. So to visualize that, let us assume that we are moving like this. So we are in discrete time, so we move by discrete steps. So we get different values of theta. At some point, our step would take us outside. This would be theta hat before applying the projection operator. So this is not allowed. So we need to get back to the domain. And the way to do this is we locate the center of this hypersphere. We take the radius going from the center through the value of theta we computed, and we go back, and we stay with the new value here. Because indeed, this is what we are doing. We are taking theta hat, that is a vector, so the direction of theta hat, and we are rescaling it by this ratio. So m over theta divided by the magnitude of theta hat. So the result of that, if you look at this expression, is a vector that has the same direction of that theta hat, but its magnitude is exactly m theta hat. So if you take this, and if you compute it, its magnitude, well, this is m theta hat. And it is easy to see that. So once you get here, your algorithm will continue computing steps and update, and as long as you are inside, they will not be projected. If you go outside, they go projected back to the circumference here. So this is the way the projection operator is combating parameter drift. So in the case of a matched fault, this shouldn't happen often because the adaptive law is making theta hat converge to the value of theta, the true theta that maybe is here. But when you have a fault that is not matched, so if fault 2 is occurring and you're looking at observer number 3, then you have parameter drift, and observer number 3 will desperately change its own parameter, trying to match something that is impossible to match, and so you can have this behavior. It is trying to get outside of the domain. And the projection operator is preventing that. Okay, so let us go back now to the residual dynamics, because we need them to compute the threshold. So we have them written out neatly. So we previously wrote them with a marker, and now you have some proper writing here. So the bottom line is that the dynamics of the residual are similar to what we had in the previous case. We still have a lambda r, the previous time step, plus delta. That is the total uncertainty. The difference is that delta now has a new term. So the ones you see here, they were there before, but this new term is the one due to the current mismatch between the fault that is present and the one that we are learning. So in this case, the fault itself is matched because the function is the same. It is only the parameter value that can be different. Okay, and also we need to remember that still in the true case, Fi is computed with y minus xi here. In the observer is computed with y. Okay, but if we want to compute a threshold, we need to bound this. Why this? Because remember, we want to falsify the hypothesis that, in this case, the fault L is present. So we compute the residual dynamics under the hypothesis that L is present, and we bound it. We compute the maximum value that the residual can have in that case. So when the residual is crossing that, then it means a hypothesis was wrong. And so this is how the threshold should be defined. So how can we bound this now? Well, we did it already previously, so it shouldn't be completely new. So we still are computing a threshold as the solution of a dynamical equation, because you remember you can use the comparison lemma and you can use bounds that you know on the uncertainty terms. So still the threshold time k plus 1 is equal to lambda the threshold at time k plus the total uncertainty. And everything is holding for the component I. So now the issue is that the total uncertainty bound that we have here should be computed by maximizing the total uncertainty absolute value over eta and psi, as we did before, and also over theta. And why we need to do that? Well, the reason is this observer is used both for fault hypothesis testing and for estimation. So when we eventually estimate the correct parameter, so when theta hat is equal to theta, and we will discuss later that actually we have no proof this is going to happen. We just hope this is happening. But let us assume it happens. Then the contribution of the parameter estimation error to the residual is 0. But before we do that, there is some contribution. And we don't want to falsify that hypothesis only because we yet have to learn the parameter. So we need to be robust to the fact that initially the parameter that we are learning is different than the true one. So if we make that drawing again of the domain theta hat al, and some way at least we can draw the true parameter here. We don't know where theta L is, but we know theta L is inside this by assumption. We don't know the value, just we know it is there. When we start up our fault isolator and estimator, the first value of theta hat L is some initial value, maybe 0. So initially there is this difference here. And this difference is the one that, if you remember, is present here. It is driving our residual. But yet, in this situation, I don't want the residual to cross the threshold. So the threshold should be robust to this difference. And so this is why we are taking the maximum over theta. Not over theta hat, over theta. Why? Because theta hat, we know it. It is the true theta that we don't know it. So the true theta is having the same role as uncertainties here. It is something we don't know. And we need to be robust to the worst case of this unknown thing. So the way to do that is based on geometry. So for eta and xi, we assume there is some known bound on them. But for theta al, actually, we also have this known bound. It is the boundary of this big set theta. So if we can take all the possible values of theta L inside here, we can compute what is the worst case of this difference. So basically what we do is take different values here, 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 and then we ask ourselves, okay, let us compute this difference. When is this difference the biggest? Because the contribution that we have in the residual dynamics is proportional to this difference. Because the shape function g is always the same. It is only the difference in front of that is going to change. Okay, well, it is not difficult to see that the biggest difference that you have is in the point that is farthest away from the current value of theta hat L. And as this is a circle, the farthest point away is on the circumference and on the opposite side with respect to where theta hat is. So in this case, is a very peculiar case, because when we start, theta hat L is in the center, so all the points on the circumference are at the same distance. And the distance is the radius of this. It is equal to m theta big hat L. In a case that is less trivial, if we are here, so if this is the current value of theta hat L, so the point that is farthest away is this one. So we take a line going from theta hat L current through the center of this hypersphere, and we got to this. position here on the circumference. So this is the point that is the farthest away. So still, we don't know what is the value of the true theta L. We just know that in the case theta L is this one, it is causing the biggest possible effect to the total uncertainty delta. So we use this to compute the maximum value of delta. And the maximum value is computed from here, from this expression that we already had before. And then what we get is a threshold computed the usual way. So we have our residual going through this mapping. So we have all the uncertainties occurring here. So we get a set, and the threshold is equivalent to having a rectangle bounding this. Because, as we said, we compute the threshold component by component. Now is the time to look at the performances of this isolation and estimation scheme that we derived. In the case of the detection observer, we characterize performances in terms of detectability conditions. So we characterized in an open form, not a closed form, what is the condition on the fault in order to be detected. Well, similarly, we can have a condition on the fault to be isolated. And it is stated by the isolability condition, which we present here in a simplified form. So if you want to see the complete form and if you want to see the proof, you can look at one of the papers that I presented in the first slide. So the papers that you see here, and well, I am one of the authors of a few of them, so it's a bit unfair that I am suggesting them. But actually here you find the full statement of the isolability condition and also a proof of that. So the isolability condition, similarly to the detectability condition, is stated in a form like this. You have on the left side a convolution sum depending on the fault. On the right side, you have 2 times the threshold. So you want the effect of the fault to be at least twice the threshold in order to be isolable. But in this case, we don't have the fault function here. Instead, we have this delta fault function, which is called the mismatch function. This is the fault mismatch function. And the fault mismatch function is a difference between the actual fault function with the beta in front of that minus the one that we learned so far. And please notice that this mismatch has 2 indexes on the top, S and L, because this is the mismatch between the true fault, we assume it is number S, and the one we are testing, number L. So this is valid for a generic L function. And this difference is telling us how different are the 2 faults. So if they are the same, this is going to be 0, pretty much 0, and there is no way this term can be bigger than twice the threshold. Said in another way, if there are 2 functions in your fault class that looks like the same, you cannot tell one apart from the other, which makes a lot of sense. The tricky thing is that, of course, you don't have twice the same function in your fault class, which would make this trivially 0. Doesn't make sense. But the problem is another. Sometimes the way they behave can be the same. You can have 2 different faults, and under some conditions, they look exactly like the same. And this delta is 0, and so this is not true. This is not holding. As a very trivial example, let us consider a light that you can turn on with a switch. So when the light is off, you have no way to tell whether the light bulb is broken or the switch is broken. If you remember, this was the example we had in the fault mode effect analysis. There is no way. So in those operating conditions, they behave the same. In other operating conditions, they can behave in a different way. So consider the case that you have the light on. If you push the switch and the light is not turning off, well, definitely this is the switch, not the light bulb. So you see, according to different operating conditions, the fault can be different or not. And the operating conditions are actually occurring in the mismatch function here inside the function g, because g is the function, if you remember in 4, g is a function of x and u. So there can be combinations of x and u such that this difference is small, and so you cannot tell one fault from the other. In other situations, the difference can be big enough that you can tell them. So basically, this difference, if you write the residual dynamics for a case of a non-matched fault, you are getting this term in the residual dynamics. So this is the term making the residual big when a fault is not matched. And you want the residual big in that case because you want for that hypothesis to be falsified. So this is the condition that guarantees that hypothesis is falsified. So the theorem is actually stating, if this is holding for all possible faults but one, you're isolating it. And actually this makes sense because we said we want to falsify all hypotheses but one. And so this theorem is telling, then you need to have this for all hypotheses but one. And the key thing is the faults need to look different. Otherwise, you don't tell one from the other. Okay, so today we presented how the approach based on the generalized observer scheme with fault isolation and estimators, one for each possible fault, work. We've shown how to learn the parameters online, and we show how to derive threshold that is robust and that allows us to do isolation. The next lecture, we will consider the case of learning an unknown fault, and we'll present a simple example.